So I will quickly give you the overview. For your assigned truss, first of all, you will compute the panel load by this example. You will perform unit load analysis for wind load and gravity load. Then I have already given you data for the live load and dead load, and this theta will be depending upon the inclination of the truss that I have assigned to you. So all of you, you will have different design data. You will compute the panel loads, panel dead load, panel live load, windward load 1 and windward load 2 if they are applicable, and leeward wind load. And then you will develop this table of forces. And I told you that you can perform unit load analysis for truss on any online software. So you can Google it, you can find many software, free software available online. And for the wind load, actually the many software, you are not having any provision for the application of inclined load. So what you can do, if you know the angle of top chord, then you can convert this unit load into two components, horizontal and vertical component. And instead of applying the inclined load, you can apply these components of the load for unit wind load. So again, this is the file that I have shared you. So in this file, I have given all the data. So this is a sine truss. So height and length of this truss is related with your registration number. R value is 900 minus N, and N is your registration number. So if your registration number is 2017 CIV 60, then N is equal to 60. Spacing of truss you can compute from this formula, and answer will be in meter. Length you can compute by this formula, and this will also be in meter. So if you know the length, you can compute the height. Height will be equal to L by 4. So you know the height and you know the half of the length, you can compute the inclination of top chord. And you can assume that top chord is divided into 1, 2, 3, 4, 5 equal length. And then you can determine this panel point by assuming that top chord is divided into 5 equal parts. Similarly, you can assume that the bottom length is divided into 5 equal parts, 1, 2, 3, 4, and 5. And you can compute these panel points for these joints. And then you can connect all these joints by this member, and you can compute the length of all members and their interior angles. So this dash line, there is no any member over it. So the dead load and the live load I have given, and you can consult LRFD design aid for the computation of the panel load. And then at the end, you need to develop this table of forces, and you need to repeat column 7 to 10 for PWW2 because you might have two windward loads. So detailed instructions are provided. And this is an example. This is one table of the forces that a student developed the last year, and I am just sharing with you. In the first column, this is the member name. You can give them the name 1, 2. He has given the name A, B, C, C with reference to the joint. So you can even assign them the number, or you can assign the alphabet to the joint. If this joint is A, this joint is B, so this member will be AB. Or you can give them the member number 1, 2, 3, 4, 5, 6, 7, 8, and on so on. So in this second column, you will write down the length of each member. And here you will write down the force in each member due to unit gravity load. In the fourth column, you will write down the member force due to the windward load from the hinge side. And then you will, in the fifth column, you will write down the force in each member, either compression or tension. If the load is wind load is acting, from the roller side. So this is the roller side and this is the hinge side. And here, these one this load combination is gravity load combination, and this load combination are live load combination, including wind load. So these are the four load combination. So in this four load combination, I have used windward load 1, PWW1. Then I need to add four more column for PWW2. I have just explained it last time in detail. And then what you will do, all the compressive forces you will put with the negative sign, and all tensile forces you will substitute with positive sign. Then the same one member, for example, this is the member AB, it is having different magnitude of the forces due to different load combination. So it means that during this service life, the structure or truss might be subjected to this 9 type of the loads. So due to each load, let me correct the numbering. So here you will write down the what is the maximum tension in this member AB due to any applied load combination. So due to any applied load combination, so due to gravity load, this member AB is subjected to a force of 108. So it is also subjected to tensile force due to this load combination, but this is not maximum. So here you have to write maximum tensile force due to any load combination. And in the second column, or column number 16, you will write down maximum compressive force, which is the maximum value with negative sign. And obviously that is this 51. So you can use the formula maximum value out of these columns, and here you can use the formula minimum out of these columns. So in this case, all the member force member, they are also having maximum tensile force and maximum compressive force also. Maybe in your case, some of the member will only have tensile force and they will not have any compressive force due to any load combination. And some of the member may have only compressive forces and they will not be subjected to any tensile force due to any load combination. So anyhow, if a member is only having tensile force, you will write down tension member. If it is only having the compressive force, you will write compression member. And then if it is having both, that member may be stress reversal, but we need to check the condition. So after that, what you may do, you can develop another table. So from this table, you will just write down this table you can copy. You can just write down the member name, length, and PU and TU, maximum tensile, factor tensile force, and maximum compressive design compressive force against which the member is subjected to due to any load combination. So where is the table of forces here? Then what you may do, actually, I have modified the same table, but you can sketch a different table also. So I will just explain from here. I just need these two columns. This is the maximum tensile force, this is maximum compressive force. So I need to check whether this is a stress reversal member or not. So whether you need to design this member as a compression member, tension member, or stress reversal. So I have already explained in tension member design. We need to check these 4 conditions. So number 1 condition, we are using the welded connection. We need to check whether TU is less than PU or not. If TU is less than PU, then that member will be compression member. So this is case 1. So in case 1, so I have written a formula here. So if you are good in programming, if you are not good, you can check manually and you can write it over here. But here I have written the formula here. So what is this formula? So this formula explains that if column number 15 O, this is O, and this 11, this is tensile force. If this TU is whether less than equal to PU, so I multiply PU with -1 just to convert into the positive value. If TU is less than PU, then he will write here as a compression member. If this condition is not satisfied, then he will write as a not applicable. So I have just written a command. Command case 1 is that if he will check if TU is less than PU or not. If TU is less than PU, he will write here as a tension member. As a compression member. If this case is not applicable, if TU is more than PU, he will write as a not applicable. So when I use this command, so this member, he automatically has written pure compression, and in the other, he has written not applicable. Not applicable means that case 1 is not applied. Okay, here in this case, you will see that this tensile factor force are less than compressive force. So this member I will design as a pure compression member. All the other, so I will not check any apply this formula where I already have the pure compression. But here, which in the where the case 1 is not satisfied or I am having not applicable, I will use the condition number 2. What is condition number 2? I will check whether the PU is less than 10% of TU or not. If PU is less than 10% TU, that member will be our tension member. If this case is also not applicable, is not satisfied, he will write down not applicable. So here, just see what I have written in the command. So P11, P, this is a P column and 11. This is the compression forces multiplied by -1 just to convert into positive. And if this is less than equal to 10%, 10% of O11, O11 is this one, TU. If this is applicable, uh, if the compression forces are less than 10% of factor tensile forces, the member will be designed as a pure tension member. If this case is not satisfied, he will write not applicable. So here he has also written maybe not applicable. It means that we do not have any pure tension member. So then in this case, what you can do, here the formula is very complicated formula he has used. So I can make this formula as a more simple, but anyhow, I will have to use the third condition. Third condition is that I will compare TU with this parameter. If TU will be more than this parameter, this member will be condition third and fourth is for stress reversal. If TU is more than this parameter, this will be stress reversal member that will be designed for tensile forces, but capacity will also be checked for compression. But if this condition is not satisfied, TU is less than this parameter, then this member will be designed as a stress reversal member, designed as a compression member, but it will be also checked for the tension. So here you will see that what he is doing. Actually, I think I forgot to start the recording. So here, just see, in this case, what formula he has used. So if you are checking this formula, just see here. this is 1 plus 0.015 into B11. B11 is the length in meter. Just see, B11 is the column length in meter, and we are taking the square of the length multiplied by minus 1 multiplied by P11, which is the factored compressive force. We need to convert into positive, and we are comparing with this O11 TU. So he is checking whether TU is more than this factor. If this condition is satisfied, he will write down stress reversal but design as a tension member. If this condition is not satisfied, then he will write as a, I will modify it here. I think no need to repeat this column. But if this condition is not satisfied, then I will write the formula only in one. Okay, let me see first what he has done. So he has written that stress reversal in tension. Is there any stress reversal in compression? So let me modify the formula same here. So I will say that if the above condition is not satisfied, then instead of writing the not applicable, he will write stress reversal but design as a compression member. Compression. So wherever we are, this formula will only be applicable. It is not applicable for this condition because we already having pure compression. Also not for here. Only for those columns where we are having not applicable in the first and second case. Is this supposed to be the here? So here, maybe you might have some different cases. So out of these cases, so you in the remarks, you have to write down the remarks. For example, this member will be designed for tension, but capacity will be checked for compression. So this member will be designed pure compression. We do not have any pure tension member, but you might have. I believe that in this table there are some mistakes. I will try to find some old table where all the values are correct. Or what you may do, any student, he can send me his own table of forces and I will check it. So I believe that some of the member must also be there as a compression member. For example, if I will write down here. So you might have some of the members stress reversal compression. Stress reversal compression means that you will be designed as a compression member, but the capacity will also be checked for tension member. So in this way, you can print out this table of forces. So either you can print out this table of forces on A3 sheet, or you can uh, print this table by parts, uh, maybe on A4. So here, these four columns. So I have already modified this table of forces last time. So these four columns are PWW, one, and these four columns are for P windward load 2. Let me make it. So in this way, you can develop the table of forces. You can divide into two parts. Maybe one table of forces until this, and second table of forces will only have member length, PU, TU, and rest of the columns. Or this will be the only Yes. So you can make this table by parts. So one table only until this remarks, until PU and TU, and second table of forces will be, you will have only member name, member length, maximum PU, TU value, and here. Okay, here what I have done here in this thing. So I have computed this parameter, PU equivalent. I'm calling as a PU equivalent just to minimize the calculation. So here I have computed this whole parameter, this parameter, and I'm calling this parameter as a PU equivalent. That is that magnitude of the compressive force which will be equivalent to TU. So I have computed into a separate called PU equivalent. So which value is equal to 1 plus 0.015 length square into compression force. So here I'm just checking with, if PU equivalent is more than TU, that will be stress reversal member as a compression. If PU is more than PU equivalent, that will be stress reversal member but designed for tension. So at the moment, anybody is having the question from table of forces? Any student is having any question? 92 roll number, are you there? Use the raise hand option if you want to ask the question. Yes, Uzair Shafiq, what is your question?
सर ये हमने सबमिट कब तक करवाना है प्रोजेक्ट अपना?
एक्चुअली प्रोजेक्ट जो है आफ्टर जो मिड टर्म के बाद जब आप आएंगे ना, तो यू शुड हैव योर टेबल ऑफ फोर्सेस कंप्लीटेड. ठीक है, टेबल ऑफ फोर्सेस और उसमें पर्लन डिजाइन जो, और द पर्लन डिजाइन दैट आई विल एक्सप्लेन टुडे, यू नीड टू डिजाइन द पर्लन एंड द रूफ शीट डिजाइन. So after the midterm, when you will come, your class will be on campus. Then I will give you the instruction regarding the connection design, and then you have to make the drawing sheet for a complete truss in our drawing classes. So your submission will be immediate after the midterm exam. So until now, what you may do, I believe that I have already given you the all instruction. So you may start the development of the table of forces. You can start computing or calculating your panel load. And today I will explain the design of purlin. So it means that you can also start designing of purlin after today's class. So in the next class before the midterm, I will explain the roof sheet design, how we can design, what type of the roof sheeting you will use, and how many number of the roof sheets are required for your truss system. Okay? You got it, Uzair?
Yes, sir.
Okay. So if you will have any query, you can send me your question. I will try to address. Okay, now today we will start the design of purlin. So have I given you all the instruction for this purlin design before? No? Here, I guess I have explained some of the portion for the purlin design.
सर वो आपने मेरे ख्याल में स्टार्ट किया था, थोड़ा सा करवाया था.
Okay, I will explain it again. Okay, in purlin design, I have need to open also maybe the lecture slide number 1. Or I have to check whether I have added the slide here or not. Okay, now. Okay, from this drawing sheet, I need to explain the purlin. For example, we are having this one truss and one truss on the other end. So this beam is a purlin, this one. Now this purlin is also a truss, smart truss. But actually a purlin is a beam which is connecting two panel points or panel point of two trusses. So length of this purlin is equal to spacing of truss. So here, so again, just assume that we are having this one truss and there is another truss. So forget about these things. I will explain these diagonal members. So these are purlins. So what is the purlin? Purlins are transversal beams. These are the beams which are provided perpendicular to the truss direction, which is connecting two panel point of two trusses. So one purlin is placed on panel point of one truss and other is placed on the panel point of second truss. So actually all type of the loading is acting on the purlin. So purlins are trusses are only in contact with purlin, and all type of the extra utilities, maybe roof sheeting and insulation board, they are placed on purlin. So it means that all type of the roof sheeting they are connected with this purlin with the help of maybe J board or maybe other type of the boards. And if there is any load, load is acting on the roof sheet, and from the roof sheet, load is transferred to the purlin. And the purlin they are transferring the load due to their end reaction on this panel point. So because truss is only in contact with purlin end, so it means that all type of the applied load is transferred at the panel point in terms of a point load, which is actually the end reaction of this purlin beam. So today actually we want to design this purlin. So we will design for the gravity load. So gravity load means that we will not consider this inclined length. We will consider the horizontal length. So actually the total load is acting on this panel. Just I'm assuming it, and also on this panel. So from this half of the panel load is transferred on this purlin and half of the load is coming from the other panel. So it means that if a total UDL load is acting on this roof sheet, if I multiply with this spacing of purlin, spacing of the purlin is equal to the panel length. So panel length is the horizontal distance between the joint in horizontal direction or the projection of two consecutive joints. So half load is coming from half panel length from the one side and half from the other side. So it means that the total length or the width of the load supported by purlin is equal to P. So it means that we are having total gravity load acting, which is in UDL. If I multiply with this P value, I can convert into UDL load. So I will explain it step by step. So actually, for the purlin, for our convenience, we will use the ASD method instead of LRFT. We can also use the LRFT, but for our convenience, we will only discuss the allowable stress design. So we are assuming that the roof sheeting provide the necessary lateral support to the purlin through J boards, and the purlin behave as a continuously braced beam. So I have added some pictures. So you will see that these are the roof sheeting, and roof sheeting is connected with purlin only. You can see these are the boards. So actually, these boards are providing along the length of purlin. So roof sheeting, they are intermittently connected with purlin with the help of roof sheet. It means that we will see in our beam topic that the beam, if they are bending in lateral direction, their strength is reduced. So here, it means that roof sheeting is connected with the help of J boards or other boards with purlin. So purlin cannot move in lateral direction. So there is no any chance of lateral bending. So we can assume that beam or the purlin is continuously connected throughout the length. So it means that we can assume continuous boundary condition for or continuous bracing of the purlin in lateral direction. Lateral direction means that along the length of the truss, the beam cannot move. So I had added some pictures. So here you can see that this is a purlin channel section. So with the help of J board, the roof sheet is connected with the purlin. So we will use the allowable stress design. I believe that last time I have explained, but anyhow I will explain it again. Let me add one new slide. Let me check if there is any equation I have added so that I could modify it. Yes, I have one equation here. Actually, what I want to explain here, I just want to explain basic design equation. I told you the basic design equation means Rn should be equal to less than equal to. Okay, let me Ru. So factored load effect should be less than equal to phi Rn capacity. This is a general equation. So this equation is in LRFT. So if we are having applied load as a MU, just like in tension member, applied load was the TU, then this should be less than equal to moment carrying capacity. So this is the equation in LRFT. LRFT means that we are comparing the factored applied load with moment carrying capacity. Actually, if we are using ASD method, in ASD method, this equation will be different. Why different? Because instead of MU, we are using the applied load due to service load. And we are not using strength reduction factor, rather we use the factor of safety omega, which is acting on the one side. So where was the omega? Yes, here. So this is the equation in ASD. Okay, MA we can compute. MA is the moment acting in purlin or in beam due to service load. Service load means due to dead plus live load. But what will be the MN? So MN is the capacity that we can compute. We know, or we already know that stress I can call it bending stress, because bending stress is our sigma. Sigma is equal to M y over I. You already know this equation. I can write this equation to like this also. So instead of writing y over I, so I over y is equal to section modulus. So this will be section modulus about x-axis or y-axis. So we will have this equation. So M is if we know the applied moment, or Mn is the moment carrying capacity. So moment carrying capacity can be computed if a beam is already designed. Then we can bring Mn on the one side. So we can use as FB multiplied by S. So this will be our capacity. So this will be the capacity. If we know the section modulus of any beam section is given, and if we know the bending strength, so FB is the material strength, FB. So we can also write as a, we can replace FB as a equal to Fy. So bending strength can be assumed as a equal to yield stress, and then this will be equal to capacity. But this capacity is the elastic capacity. So it means that if I am comparing, I will substitute the Mn value in this equation. So let me call this as a equation number one. So in this equation number one, if I am comparing allowable applied service moment with the capacity, then equation number one will become MA will be equal to Fy into S divided by this omega. And you can refer as a, this is equation one implied. So this will be our design equation, but I will further modify this equation because we know that F, we have already seen that factor of safety in ASD we are using 1.67. If we know the Fy, we can assume this S value. But here, there is one more modification that you will see in the slide. Actually, I have explained that, just mentioned, roof sheeting is continuously connected or intermittently connected with the help of board with the purlin. So we are assuming that purlin is continuously braced in the lateral direction. So there is no any chance of lateral bending in purlin. So this thing we will study in detail our beam design topic. So in the beam design topic, we will say that if a beam is not appropriately braced in lateral direction, lateral mean horizontal, not in vertical downward direction, lateral, then it can fail at a load value less than Sx. So we assume that if it is continuously braced, then instead of using elastic section modulus, we have to use the plastic section modulus. So if for continuous lateral bracing, we can assume that in that case we will have plastic stress distribution, and for the case of plastic stress distribution, we have to consider actually this formula. M A will be equal, instead of plastic section modulus, we have to consider as a plastic. So this will be about the x-axis, because beam is always bending about the x-axis because the gravity load are acting. So Zx is the plastic section modulus. So this thing, plastic section modulus, I will explain when we start the beam topic, when we will have the on-campus classes. But for the time being, you can assume that if a beam fail at a stress value more than Fy, so instead of using the elastic section modulus, we supposed to use the Zx plastic section modulus. So plastic section modulus is always more than Sx. But here we are assuming that in our case, this value is equal to this one. So 1 over 1 over 1.67, that is equal to 0.6. And we are assuming that Zx value, that value actually equal to 1.1 time of elastic section modulus. So Zx value is equal to 10% more than Sx value. So in this case, if I will modify the formula, so MA will be equal to 0.66, because if you multiply 0.6 with 1.1, answer will be 0.66, and Fy into Sx. So this is the our design formula. So in this case, if we know the applied bending moment, if we know the material strength, only unknown will be Sx. So this is actually how I have derived the formula, which is basically depending upon our basic design equation. Now I will explain from here, that is given in the book. So MB, bending strength, bending capacity. So I have written here Mn. You can write down MB also. This doesn't matter. So bending strength is equal to FB, bending strength, multiplied by plastic section modulus divided by factor of safety in bending. So FB, I'm replacing FB with Fy. 1 divided by 1.67 is equal to 0.6. And we, for the plastic stress distribution, I'm assuming that Zx is equal to 1.1 time of the Sx. So bending strength here, it means that that is equal to 0.66 Fy. And in case of the tensile stresses, tensile strength is equal to Fy. So forget about this, because in our tension member design, so we are not increasing the tensile strength by 10%, but only in bending strength. Forget about these two equations. Just remember how we have derived this formula. So now we can compare this equation MB, bending strength, with the service moment. Then only unknown will be Sx. So if we know the service applied bending moment, if we are given with the material strength, we can determine what is the section modulus required for this purlin, that we can compute easily. Okay, now dead plus live load combination will be used because it is proved to be critical for purlin and roof sheeting design. So we will not design the purlin for wind load. We will only design for snow load and the dead load dead load. So dead load plus live load combination or gravity load combination will be used. So wind load will not be critical, because if the wind is blowing, due to wind, there will be uplifting effect. Gravity load effect is downward and wind load effect is upward. So it is negating the gravity effect. So if the wind is not blowing, then the purlin is subjected to maximum force. So due to this reason, we will only design for gravity load combination without being multiplied with any factor of safety, because we are using service load. Dead load on purlin acts due to what type of dead load which may act on the roof sheeting. So purlin is roof sheeting is connected with the purlin. So purlin is supporting the roof sheeting, insulation panel, and also the bolts. So it means that in order to compute the dead load on the purlin, we are not considering self weight of the truss. Self weight of the truss is not acting on the purlin, because load is coming from the top direction and it is moving in the gravity direction. So dead load, we will consider dead load I have already provided to you. For example, in your case, you will use this dead load. Dead load of roofing, self weight of the bracing element, insulation panel, and miscellaneous load you will use. These loads are the load which are acting on the purlin. So you will not add the self weight of the truss, because self weight of the truss is not acting on the purlin, but purlin load is acting on truss. Then approximately 1/3 or half of the miscellaneous load may also be included. So in the panel load computation, we assume full miscellaneous load. So what are the miscellaneous load? Miscellaneous load means the load of the bolts, washers, nuts that we are using to connect the roof fitting with the purlin. But actually we are also using many bolts in order to join the truss member with the guzzler plate. This means that for the purlin design, no all bolts load is not acting on the purlin. So we may consider maximum miscellaneous load from 1/3 to half. So you can consider from half to 1/3 of the miscellaneous load for the design of purlin. Actually, I told you that whenever we design any structural component, especially the beam, we also design for serviceability state. So serviceability state means that the deflection due to applied load in deflection in the purlin due to applied load should not be more than certain limit. So it means that if deflection should be less than allowable. So it should, so deflection is always resisted or controlled by moment of inertia. So moment of inertia of any section is depending upon the depth. So at the start, what we do in order to avoid the uh, failure of the deflection check, we try to select a section which is having sufficient depth. So to maybe satisfy the deflection criteria at the end. So at the start to reduce the number of trials, so we are keeping the D minimum. So minimum depth of the section should be more than span or this length of the purlin divided by 27.5. So length of the purlin is equal to spacing of the truss. So in other words, depth, minimum depth of the purlin should be more than span or the length of the purlin divided by 27.5. So we want to make sure that the purlin should have sufficient depth so that it can also so that all the deflection should be within allowable limit. So S is the spacing of truss, and spacing of the truss actually equal to the length of purlin. So this is the order of designing the purlin, or this order for the selection of purlin. So in the previous code, the design of the purlin was very lengthy procedure, but now it has been simplified. So sometime I told you that we brace our beam in the lateral direction, and bracing is provided in terms of sag rod. Just like here, this is the sag rod, which is supporting the purlin in the lateral direction. So this sag rod, actually this is the lateral bracing for this purlin. So these sag rod, actually they are not letting this purlin to move in the lateral direction. So sometimes we brace it, we provide one sag rod along the length of the purlin, or sometimes we provide two. So in the previous slide, you can assume that this is one truss and this is second truss. And these member, additional member, these are the sag rod. So we have used 1, 2, 3 sag rod to break up the total length of the purlin. So these sag rod, actually, these are also connected with the top chord, top member, and also bottom member. They are not letting this purlin to move in the lateral direction. So if we are breaking up the purlin into different segments by providing the sag rod which are constraining the lateral movement, so design will be economical. So how many number of the sag rods we need to provide, so we can decide based upon these guidelines. So what are these guidelines? So if inclination of our roofing system or top chord is less than 15 degrees, we will not provide any sag rod. And if inclination of our top chord is more than 16 degree and less than 25 degree, what inclination? This angle of top chord with reference to the bottom chord. So this angle you have to compute. So we will design with one sag rod. And if inclination is more than 25 degree, we will always initiate the design by assuming two sag rods. So at the start, we know the angle. So we will try to select single angle section as a purlin using maybe any appropriate number of the sag rods. If single angle is not satisfied, then we can go for channel section. And if the channel section is also not sufficient, then we can go for W section. But for your practice class, you will design the purlin by considering the single angle section and also C section, both. So you will design by using the appropriate number of sag rods. Again, I am explaining, you will also design purlin by assuming single angle section and also channel section. Then whichever will be the lighter one, we will use that channel section or angle section as a purlin in our case. But if we are designing the angle section as a purlin, then the width of the angle section should be less than 102 millimeters. So why this condition is there? Because if we are having any angle section, let me check. Okay, let me explain from here. Let's go this angle we are using. So here. Cursor is not appearing. So for example, you can see that this one angle only considered. One leg is vertical and one is horizontal. So vertical leg is placed in the transversal direction, and this is shorter leg is placed to support the roof sheeting. So in this case, this shorter leg, the width should not be more than 102, because we know that center of gravity of the angle is outside. So if the width will be more, so and center of gravity will be more outer side. So it means that if it will be for the larger width, center of gravity will be away from this vertical leg, so which will have secondary effect. Secondary effect means that all the load are passing through the center of gravity, so they will tend to produce the rotational effect. So in this case, the width of the angle section is limited to 102. 102 means around 4 inch. Vertical leg, longer leg, it may have any length, any dimension. So it may be more than 102, but this shorter leg, which is supporting the roof heating, it should be less than 102. So Z section behavior-wise is the best section for the purlin. So Z section is the most economical, which is having Z-type shape. So normally these are cold work sections, which are made out of steel sheet. We are pressing at room temperature. So why this Z section is more appropriate, inshallah we will study in the sixth semester. So next guideline. In case section modulus required for the first option is greater than 230 into experiment 3, then we will not select the angle section, we will directly move to the channel section. So we will may use channel section as a purlin. If section modulus is less than 230, we may select the angle section as a purlin. But if required section modulus is more than 230 into exponent 3, so we supposed to use channel section. So width I have already explained. So how to compute the UDL load? So Purlin will be designed a beam which is subjected to UDL load. So all type of the load that we are given, just like here, are UDL load. Where are the loads? Here, kilogram per meter square. So we need to convert this load into the UDL. So we will multiply this load by the total width of the roof sheeting supported by a purlin. So I have already explained that. So one purlin, if a total load is acting in this panel, half load is coming on this purlin and half load is going to the other purlin. So we will design the interior purlin. This means that one purlin is supporting half of the width, panel width from the one side and half panel width from the other side. So half P from the one and half P from the other side, it will be total P. This means that if we multiply the total UDL load with purlin spacing is equal to the panel length. Panel length, that is the distance between two, horizontal distance between two consecutive panel points. So in this way, we can convert into UDL load. Note, what if the panel length is excessive and it is difficult to design the roof sheeting purlin are also placed in between the panel point to reduce the purlin spacing and span for the roof sheeting. So this induced bending moment on the top chord. So let me explain what it's saying. Actually, he says that, so we are having some total maximum length of the width, sorry, maximum width of the roof sheeting available in the market. It is having some certain length. So if the length of the roof sheeting is very large or panel length is very large, so it means that we cannot cover this spacing with a single roof sheeting. So sometimes we will can also place, to reduce the panel length, we can place the purlin on the top chord. So if the purlin they are placed directly on the top chord instead of placing at the panel point, then we need to design this top chord as a beam, because the end reaction which is transferred on the top chord will behave as a point load which is acting in the center of the beam. Because if the line element is subjected to any transversal load, so this is referred as a beam. So in that case, we have to design the top chord member as a beam. But what we do at the start, we are keeping the panel length less than the total width of the sheet, roof sheeting available in the market. But if there will be any case, if we are placing the purlin on the top chord instead of placing at the panel point, so we need to design the top chord as a beam. So lateral component of the load at the top flank produced torsion should be considered separate from the self weight of the purlin not producing torsion. Okay, here. Actually, we are having two type of the dead load or two type of the applied load. So let's assume that we are having this as a purlin, W section, and this is also W section. So you have seen in the previous diagram that roof sheeting is connected on the top of purlin. So load is acting in the gravity direction. Okay. So I want to explain. So what we may do, we can Just for your understanding, I would like to change the color. Blue will be okay. So all type of the load is acting in the gravity direction, and roof sheeting is placed on the top part. Actually, it means that this purlin is inclined because this is placed on the top part, which is inclined. So all the dead and live load, they are acting at this top point. So if this is the centroidal axis, I may assume. Yeah, this is the centroidal axis. So all the load which are acting on the top part, which is the snow load and dead load, because but the roof sheeting is connected on the top panel. So if I can convert this applied load into two components, one component of this load is acting parallel to this plane and one is acting parallel to this web. So this component of the load, it is passing through the centroid, so it is not producing any movement. But this component, which is acting in this lateral direction, so it is having certain eccentricity from this central axis. So this component of the load, which is acting on the top or the top surface of the purlin, it is producing the torsion. But the self weight of the purlin is acting at the center of gravity, and both the center of the gravity, if I am converting into component, are also passing through the torsion to the centroid. So they are not producing any twisting. So it means that the load which is acting or which is coming from the top of the purlin, so one component of that load is producing the torsion. And let me write here. So this component of the load, if I'm transferring here, it tend to produce the bending. The load component which is acting in x direction will produce the bending about y-axis. So this will produce the bending stresses, bending moment about the y-axis. This component will, which is acting along the y-axis will produce the bending moment about the x-axis. Plus this component will also produce the torsion. It means that in that case, the total stress in this purlin will be bending stress due to the movement mx, bending stress due to the movement about y-axis plus torsion stresses. But cell weight is not producing the any extra stresses because both component of the self weight, they are passing to the centroid. So we are assuming that the self weight is not producing any torsion. So what we will do, we will keep the self weight of purlin separately and all the other dead and live loads separately for the computation of stresses, because applied dead load and the live load which are transferred from the top surface, they are also producing torsion along with bending moment about x-axis and y-axis. But the self weight is only producing the bending moment about y-axis and x-axis. So in that case, in order to compute the actual stresses, we will keep the self weight separately. So whatever he say, lateral component of load at the top flange produced torsion should be considered separate from self weight of the purlin not producing torsion. So the load which is acting on the top flange is we are computing separately and self weight separately because self weight is not producing torsion, but the load which is coming from the snow load, dead load or live load, it is producing the torsion. So this component of the load which is acting along x direction is producing the movement about y axis, And this load component, which is acting in y direction, will produce the moment about y-axis. And in this case, we are also having additional, you can say, torsional stresses. Okay, let me modify this slide again, just for your explanation, if you could understand. Okay, here. I will try to explain. After this explanation, we may have break. I told you that when we design, after designing, we need to compute the total stresses in our section. If applied stresses are less than material strength, our design is okay. Total stresses, FB, I'm writing it here as a FB, total bending stresses in our beam in case of purlin, because this is subjected to biaxial bending moment. Why biaxial bending moment? Because we are having load component which is acting in x direction and also y direction. Load which is acting in y direction or along the y axis of section is producing a moment about x axis. And the component of the load, because load is inclined, which is along the x direction, it will produce the moment about y axis. And also this component will produce the torsion about longitudinal stress. So our equation will be bending stress, total bending stress will be equal to the bending stress due to moment mx or here I will just first write down, then I will modify it. So stresses due to mx. I am writing it so that you will later on, if you will see the video recording, you may understand. So bending stresses which are produced due to the moment of acting about x-axis. Bending stresses which are produced due to the moment acting about y-axis, plus bending stresses which is due to the moment acting about the z-axis. Z is the torsion, because that is the moment which is produced about the longitudinal axis, and this moment is the produced due to this load component about the centroid, and moment arm will be half of the depth, and this is also producing the twisting. So total stress can be computed. So stress due to mx, we know we compute as a mx by ix. So bending stress due to mx is equal to my over ix. So these are the stresses that we can compute. And stresses due to the my, these are the due to the moment my, and due to the moment my, the stress will be distributed along the x-axis. And moment of inertia we supposed to use Iy. And in the mechanics of material, due to the mz actually you can also write torsion. So due to torsion, stress are computed as these are the shear stresses which are computed by as a into rho for radius rho over j. J is the polar moment of inertia. We are computing the, so tau mean that you can either write tau, torque, or you can write as a mg. So mg is the torsion. If the moment is produced about longitudinal axis, that is referred as a torsion. So you can present this. So tau rho over j. J is the polar moment of inertia, which is j is equal to ix plus iy. Actually, what I want to explain here, I want to explain that because we want to design and it is very difficult to compute these torsion stresses. Torsion stresses are easy to compute, uh, easy to compute for the rectangular section and circular section. But for any open section, channel section, angle section, and eye section, it is difficult to compute torsion stress. Okay, let me also modify this formula. So instead of this, I can write as a Sx because I over y is equal to Ix, and similarly I can write as a Sy just to modify. And here Mz is equal to torsion, both are the same. So torsion stresses are difficult to compute. So for the simplification, what we assume that the torsion stresses are same, having the same magnitude as of stresses produced by the moment about y-axis. So for the simplification, if the bending moment about x-axis is producing the stress 100 and bending moment which is acting about y-axis is producing the stress 50, we are also assuming that the stress produced by torsion are also equal to 50. So I'm also assuming this stress component or changing this value equal to this value, same value. So if I will further modify this formula, so for simplification, we assume that torsion stresses are also equal to the stresses produced by My. So if I can multiply it by 2, so these are the total bending stresses. Or you can bring this to at the bottom. So or you can assume that about Sx section modulus about the Xx is taking the moment about X-axis, but we are using half section modulus about Y-axis for My, and half is reserved for the torsion. We can see that if you are having glass, half glass capacity is for the torsion and half for the will be used to utilize the bending moment about the y-axis. That is simplification. So we are not computing the torsion stresses directly, but we are assuming that torsion stresses are same as of the stresses produced by My. So in other words, we are assuming the half of the capacity about y-axis in due to the bending moment My and half for the torsion stress. So here, now if you will read this, you will understand. In place of using complicated formula for torsion design or for the stress computation, torsion stress computation, we are assuming that half strength in lateral direction, lateral means about y-axis. Half strength means we are using half section modulus is reserved for torsion and other half will be used Sy by 2 for My or for to resist the bending moment about the y-axis. No calculations for torsions are required afterward. So we are not computing actual torsion stresses because they are difficult to compute. So that is assumption. So I have explained to you. The total bending stress will be due to the Mx, My, and Mg torsion. So bending stress due to the Mx will be equal to Mx over Sx. Bending stress due to My will be Sy over Y, Sy. and the torsion stresses are equal to tau rho over j. So we are assuming that tau rho over j is also equal to bending stress about the y-axis. Or we are assuming that half capacity or half section modulus will be used to resist the bending stress due to my, and half section modulus about the y-axis will be used to resist the torsional stresses. Purlin is assumed to be simply supported on trusses both in x and y direction bending, and the bending moment may be calculated by using the typical bending moment diagram given in reference 1. Let me see how many slides. Yes, only 2 slides are to explain. So in this case, so we are assuming that our purlin is simply supported between two trusses, also in downward direction and also in the lateral direction. Why in the lateral direction? Because this purlin is subjected to biaxial bending, because the applied load is inclined, so we need to convert the load into two components. One is acting in the lateral direction and one in the gravity direction. So the load which is acting in the downward direction will produce the movement about x-axis, and the component which is acting in the lateral direction will produce the movement about the y-axis. So sag rods are also considered as a roller sport or interior sport. Okay, here let's assume, forget about this one and this member. Assume that we are having only one sag rod. If sag rod is used, sag rod are not controlling the bending about y-axis. So about the y-axis, we have to consider the total length. But in y-axis, if it is bending in this lateral direction, so actually this sag rod is controlling the bending in the lateral direction. It means that in this lateral direction, we are having one extra support. So it means that in this lateral direction, our purlin is continuous beam, which is having two spans. Ends are simply supported, and sag rod is behaving as a roller support. So it means that for this purlin about y-axis, this bracing will not be effective, and we are assuming that whole length of the purlin. So this point is showing the lateral bracing. So along the major axis, it will bend as a whole. About y-axis, so this sag rod will behave as a simple support. So it is a continuous beam about minor axis or about the y-axis. If we are having two sag rod, then we will have a purlin which is having three spans. So this formula I have already explained. Mx over Sx are the bending stress due to the Mx. My are the bending, My over Sy are the bending stresses due to My, and the torsion stresses. And the torsion stresses will also be assumed as a My over Sy. So if we are having for an ordinary beam where only Mx is present, if so for them, if the applied stresses are only Mx, so if Mx, these stresses are 0, so Sx will be equal to Mx divided by Fb. So if we know the bending strength of the material and Mx is given, then we can determine how much section modulus is required. Actually, this thing I have already explained from in this case. So if we know the applied bending moment, so this 0.66 Fy is the bending strength. So Sx can be determined. Sx required will be equal to applied bending moment divided by 0.66 Fy. Okay, however, in case of purlin, for this case, when we are having two unknown, Sx and Sy, in that case, we need to convert it into the equivalent single section modulus. So we convert Sy also into the Sx. So this thing we will use in our purlin design. So here I would like to have a 10-minute break only, 10 minutes only, because after the break I will explain the design procedure and we will start the design of the purlin. Discussing the different types of the specification regarding purlin design. Now we study the purlin design procedure in detail. So in the first of all, the first step is that we need to compute total dead load and the live load which is acting on the purlin. So load will be computed in Newton per meter. So this load will be equal to, if we are having load on the roofing system plus insulation load plus part of miscellaneous load. So loading on roofing system may be roof sheeting load, insulation panel load, and part means we may consider half or 1/3 of miscellaneous load. So actually all these loads are Newton per meter square or in kilogram per meter square. So you can convert into Newton per meter square. So we need to multiply with spacing of purlin, which is equal to panel length. So if we multiply with the purlin as spacing, I think there is something, and then plus we need to add the self weight of the purlin. So self weight of the purlin we will assume certain weight, and again we need to multiply the self weight of the purlin by the spacing of the purlin, so that we can convert it into the UDL load. So UDL load multiplied by purlin spacing, which is equal to panel length in our case. So that will be total dead load which might be acting on the purlin. The two terms are kept separate as one is producing the torque while the other is not. So actually what we are doing while computing the load, so we are keeping the self weight of the purlin separate. So only let me highlight only this. So we are keeping the self weight of the purlin separate and all the other dead loads separate. Why? Because all these type of the load, they are producing bending moment along with torsion, and the self weight is only producing the bending moment without torsion, because self weight is acting at centroid point, just like I have explained. So this is the load which is acting on the top line, which is the insulation load, roof sheeting load, and miscellaneous load. And the gravity load or self weight is acting at the centroid point, which is not producing any torsion. So live load actually this will be the snow load that you have already computed or you have considered depending upon the inclination of the roofing truss. We will also multiply with purlin spacing just to convert into UDL load. Again, self weight of the purlin is kept as a separate. So in the previous equation, we have shown as a separate entity. We will compute WX UDL load about x-axis and UDL load about y-axis if we know the inclination of roofing system. So this theta will be equal to the theta of the angle, the inclination of roof truss. So this value will be equal to this theta value, inclination of our roofing system, that you can compute depending upon the length and the height of your truss. The total load will be converted into the x component and y component. Then we can compute the moment due to the x component and y component of the applied load. Calculate maximum value of the mx and my by using bending moment diagram for the given sag rod cases. For further calculate my for the load producing torsion and load not producing torsion. So all type of the load, self weight, the horizontal component, x component of the self weight and x component of all the applied load, they are producing bending moment about x axis. But the self weight is only producing the bending moment about the y axis. But the lateral component of all the applied load is also producing the torsion along with My. So we are keeping the both terms separate. You will see in the solution. So actually how we will compute Mx and My, we have to use a bending moment diagram which are provided in our LRFD design 8. So I will show you in the upcoming slides. So actually we are having two bending moments, Mx and My. So it means that we will have two unknown values, section modulus about the x-axis and also section modulus about the y-axis. So it means that we cannot determine two unknown values. So for the simplification of the calculation, we will convert our My also into the equivalent Mx. So what we will do, we will assume that our Perlin is only subjected to Mx and My is equal to 0. So how we can assume compute the Mx assumed value? If we are designing Perlin as a single angle unequal leg Perlin, then Mx assumed value will be equal to Mx plus 4 times of My. So it means that we are converting My into the equivalent Mx value. So we are not dealing Mx and My separately. So we are converting both parameters into a single movement about x-axis. So most of the cases we always design a single angle unequal leg Perlin. So equal leg Perlin is not recommended because if we are having unequal leg, so vertical leg will be placed along the depth direction and the shorter leg will be placed uh, maybe in transversal direction or parallel to the top chord. So if we are designing Perlin as a single angle unequal leg Perlin, then we have to use this formula. So we will convert the Mx and My into the equivalent Mx. So similarly, if we want to design as a channel, so Mx assumed value will be equal to Mx plus 15 times of My. And if we want to design Perlin as a equal leg angle section, so Mx assumed value will be equal to Mx plus 2 times of My. And if you want to select W section as a Perlin, then Mx assumed value can be computed as Mx plus 6 times of My. This equation I have already explained because we have derived this equation earlier. So yes, this one. So we will assume that MA is equal to Mx. This is the applied bending moment about x-axis. And we will equate with the bending capacity which is 0.66 Fy. So Sx is unknown. So Ma is equal to Mx assumed, which will be divided by 0.66 Fy. So only unknown will be Sx required. So Sx required section modulus about x-axis required will be equal to Mx assumed that we have just computed in the previous equation, and we will divide by the bending strength. Bending strength is equal to 0.66 Fy. So we have already derived the equation for this. So Sx required, depending upon this Sx required, we will select this section from section properties table. We will try to select a section whose section modulus about xx is more than this value. And further, during selection, we will also make sure that depth of the selected section is more than length of the Perlin divided by 27.5 in order to satisfy reflection criteria. After selecting the section that we have selected, we have to check the bending stress or the strength of section. The applied bending stress should be less than bending strength. So applied bending stress can be computed by this equation. So bending stresses are equal to mx over sx, my over sy by 2 with torsion, and my over sy without torsion. So why we are dealing with torsion and without torsion separately? So here we are computing the bending stress due to self weight separately, because self weight is not producing any torsion. And here we are computing uh, because all the applied load excluding cell weight is also producing the torsion along with bending stress. So actually this equation is equal to my over sy 2 multiplied by. So why, if 2 is coming on the top side, this will become 2. Why it become 2? Because we are assuming that the torsion stresses are also equal to the bending stress about y-axis. And then we are adding additional bending stresses due to my due to self weight. Always consider magnitude of mx and my without their sign. Mx and my may be negative, but we have to consider as a absolute value in calculation because each combination gives addition of stresses at some point and within this section. So we always need to consider absolute value. If the stress due to my is more than 2 times of the stresses due to mx, then we need to revise this section. So it means that if this component is coming out to be double as of this component, it means that stress due to the my are more. So we will divide because there are chances that the section will be weak about y-axis. So there is more bending stresses about y-axis. So you will see when we will start designing our problem. So in that case, what we can do in order to reduce this bending stress about y-axis, we can increase the sag rod. Initially, if we haven't provided the sag rod, we will provide one sag rod. If we have initiated a design with one sag rod, then we will increase the sag rod to the 2. And then if it is not satisfying with the 2, then we will move from angle section to channel. And if the channel section is not satisfying, we can move to W section. Or we will try to select a section which is having larger SY over X ratio as compared to the previously selected section. However, sag rods are limited due to construction difficulty. The first option is not employed. So we can, at some time, due to some limitations or the design constraints or the construction constraint, we cannot provide the sag rod. If we cannot provide the sag rod, then we need to select a section which is having SY over SX ratio larger than the previously selected section. So bending stress should be less than equal to 0.66 Fy. So this 0.66 Fy, actually this value is coming from this equation. So actually MA, these are the bending strength. Bending strength is equal to bending stress multiplied by Sx. So this value 0.66 Fy is the maximum or allowable material stress. So allowable stresses in ASD in case of bending are 0.66 of Fy. And then we need to check the local buckling. I told you that whenever we are the compression member, steel member are subjected to compression, there are chances of local instability or local buckling. So in case of the beam, actually when it is subjected to bending moment, so half of the beam section is in tension and half is in compression. So we might have some neutral axis. So one side of the neutral axis is in compression and other side is in tension. So the side of the section which is in compression or the flanges or the leg of angle section which is in compression, there is a chance of local buckling. So local buckling is controlled by limiting the B over T ratio. If B over T ratio is less, then there is a chance of local buckling. So in case of the channel section, we are computing VF over TF value and we are checking that that value should be less than lambda P. I think the lambda P value here will be 15.8. So we need to make sure that B over T ratio value of our selected angle section or channel section is less than lambda P. So lambda P value I believe is the 15.8, we will see. So that value is 10.7 in case of the purlin design. So for single angle, only shorter leg is in compression throughout and hence is to be used as a to compute the lambda value. I told you that when we are selecting the single angle, so vertical leg is placed in gravity direction, so which will be in tension. So the leg which is in transversal direction is always shorter. So shorter leg is in compression. So we check B over T ratio of the shorter leg in case of angle section. But in case of channel section, lambda value is equal to BF over TF. And for W section, lambda value is equal to BF over 2TF value. So we will also discuss this in detail in our compression member design. So lambda p value for unstiffened element is 10.7. So lambda p value should be less than 10.7 in our case. And for the unstiffened element, this is 31.6. So unstiffened element is the part of steel section which is only connected from the one side. So legs of the angle sections are only connected from the one side, so that are unstiffened. Similarly, flanges of channel and I section are also connected from the one side, so they are also as a considered as a unstiffened element. Then we will also check the self weight. Actually, at the start we have assumed certain self weight of the purlin. So actual self weight of the purlin should be less than assumed value. If actual weight after designing is more than assumed value, it means that we need to revise the design because we started the design with a lesser load and actual weight is more. So how to compute the actual self weight? So that they can be computed by this formula. So weight of the purlin in of the section. So this weight is given in from we can consult from section properties table, from the designation of our section, which is kilogram per meter. So kilogram per meter we can multiply with 9.81 just to convert into Newton and meter. And if we multiply with the number of the purlin, the number of the purlin means that actually we have assumed a total UDL purlin load. So if we will see that how many purlins are there. So if we are having 5 purlin, we will multiply with the number of the purlin and we will divide it by the spacing. Also the span of the truss. Span of the truss means the total length of the truss. So we can convert this load into a UDL load. So I will explain from here also. So we know the weight of the one purlin. For example, weight of this one purlin is 100 kilogram per meter. So we can convert into Newton multiply with by multiplying with okay weight is 10 kilogram per meter. G value I'm assuming as a 10 also. So if I multiply the 10 kilogram per meter with the 10, then the weight of a purlin will be 100 Newton per meter. So that is per meter. So how many purlin we are using? 1, 2, 3, 3 on the other side, and this one 7. So total load multiplied by 7 and then divided by length. So if we are dividing it by length, so we are converting this load into distributed load. Why we are converting into distributed load? Because at the start we have assumed distributed load of a purlin. So if actual load is less than assumed load, our design is okay. Otherwise, we need to revise. So assumed load multiplied by 1.2, it should be more than the actual load. If actual load is more, we need to revise the design by considering the larger self weight. Okay, at the end, we also need to design the sag rod. So sag rod will be designed in this sag rod. Okay, before the sag rod design, let me explain how we will compute the forces in sag rod and this bending moment. Actually, if you open page number Yes, page number 79. If you open the page number 79 on LRFD manual, then you can see this diagram. So there will be two cases. I will come up this Sagro design later. So at the start, if we are designing our purlin without sag rod, without sag rod mean that there is only this truss and also this truss. We are not having this staggered 1, 2, 3. It means that purlin is only braced or connected at the end when we are considering the bending about x-axis and also about y-axis. Due to gravity load, purlin tend to move downward direction. Due to lateral load, this purlin tend to move in horizontal direction. Movement in horizontal direction means bending about y-axis. Movement of this purlin in gravity direction means bending about x-axis. So it means that no sag rod is used. So purlin is assumed to be simply supported between two trusses about x-axis and also about y-axis. So in that case, you need to consider this chart. So in that case, without sag rod, mx will be equal to omega cos s square by 8 and omega sine s square by 8. What is the s? S is the length of the purlin, which is equal to spacing. So what is w cos theta? Actually, w cos theta is the vertical component or the component of the applied load which is along the y-axis. So this we are having this load. So if we are multiplying with this theta, so this wy. So wy will be equal to w cos theta because the side from which the angle is given will behave as a or serve as a base, and other component will behave will serve as a vertical component. So the component along the base side will be the cos function. So omega y is the vertical load which is acting parallel to the web will produce the movement about the x-axis. So movement about the y-axis will be produced due to omega y. So omega y is equal to omega cos theta. And this component omega x that will be equal to omega sine theta. So even though you can write over here also. That will be omega sine theta. And similarly, you can also write here. So that is dot over here. So that component will be equal to cos function. So you just need to compute W and W omega y or this omega y is producing movement about x-axis and omega x component will produce the movement about y-axis. So when we are not using any sag rod, so it means that purlin is not supported at any point along its span. So mx and my will be computed by this. So s is the length of the purlin. Length of the purlin is equal to spacing between the trusses. So when we are using one sag rod, so we are assuming that sag rods are not effective because they are not providing the vertical direction. So member will be free to bend as a whole about x-axis. So in that case, if we are using one sag rod at mid-span, this is the bending mode diagram for mx and this is the bending mode diagram for my. So the maximum bending moment will be equal to omega cos theta into s square by 8. So mx can be computed by this relationship. And about the y-axis, so this is the sag rod which is used in the lateral direction. So we are assuming that in the lateral direction, our purlin is the continuous beam having two spans. So this sag rod will behave as a interior support. So bending moment diagram for continuous beam with two span is like this. So in that case, about if we are using one sag rod, maximum bending moment will be this negative. So my will be equal to omega sine theta s square over 32. And this is the 5 by 8. This is the force in the sag rod in horizontal direction. This 5 by 8 W sine theta s will be the force in sag rod in horizontal direction. I will explain here horizontal direction. Horizontal means perpendicular to the length of it is along the length of truss. And if we are using two sag rod, third point sag rod means two sag rod. So about the x-axis, sag rods will not be effective, so mx will be remain same. But if we are using two sag rods, one is provided at each one third point. So we are assuming that our purlin is a continuous beam having three span in about y direction. So in that case, the bending moment diagram for a three span continuous beam subjected to UDL load is this. So in that case, we will assume that uh, what is the maximum bending moment? So maximum bending moment will be omega s sine theta square over 90. So omega y will be this one. And 11 by 30 W s sine theta is the force in the sag rod. So this is how we will compute mx and my depending upon the number of sag rod. And how to design the sag rod? So sag rod actually this is the uh, force in the sag rod. R is the actual force in the sag rod, and that F is the horizontal force, which is horizontal component of this force, which is developed in the sag rod that we are obtaining from this chart, which is given on page number 79 and 80. So let me explain. Yes. So let me explain. Actually, F2 force is providing incoming in direction 2. The chart which are given on the page number 79 and 78, that is providing the force in two directions. But actually the sag rod, they are provided inclined. So this inclined direction, you can assume that is the R value. If you know this F value in direction 2, you know the theta. So this F and this R, F over R is equal to theta. So R will be equal to F value divided by theta. So it means that sag rod force, with this force we will compute or we will check from the charts given on the page number 79 and 78, and that is the horizontal component of the sag rod, and we will compute this R value by dividing the F over cos theta. So R is the reaction in this sag rod and F is the force which is developed in the direction or in the lateral direction, which is actually uh, uh, in the y direction of our section. So if we know this force, so we can also design the sag rod. So that we will see in our example. So this is the example number 2. This example is given in the book. So example is that design a channel section purlin with midpoint sag rod. This is already directly given. For Actually, I had also modified one example. Yes, I need to consider this example. Design a channel section Perlan for following data. So data is given. So we are given the dead load of roofing, which is 17 kilogram per meter. Insulation panel load is given 5 kilogram per meter. And at the start, we are assuming self weight of the purlin equal to 12 kilogram per meter square. So actually, I have already provided you these loads. So you will consider the load that I have provided you over here. Miscellaneous load, I have provided you 5 kilogram for your truss design. Insulation board load, I have provided 6 kilogram. And dead load roofing is provided as a 17. So self weight of the bracing system, you also need to assume. So approximate, so at the start, we will assume the self weight of purlin also. So self weight of the purlin is assumed approximately 15% of all applied load. So you can also assume this, or the load that I have provided, you can consider the same load. Live load, this load you will compute depending upon inclination of our roofing truss. So in this question, our inclination is given as a 30. So if inclination of the roofing system is more than 30 degree, so we have to assume a snow load of 60 kilogram per meter square or 600 Newton per meter square. So this snow load will be as per inclination of your roofing truss. But here, if the inclination of roofing system is 30 or more than 30, so snow live load will be 60 kilogram per meter square. Or if you are assuming G value as a 10, so this will be 600 Newton per meter square. P is the panel length, that is the spacing of our trusses, spacing of the purlin, and S is the spacing of truss, that is equal to length of our purlin. And N is the number of truss panel. Number of truss panel means we are having 1, 2, 3, 4, 5, and 6 panels. Just like in this case, we are having 1, 2, 3, and 4 panels. So 4 panel means that this can be used to compute the total length. So this is having 4 panels, and each panel is, if each panel is 2.5, so total length will be 2.5 multiplied by 4 or 10 meters. And number of trusses panel are 8. So 8 multiplied by 2.5. So total length of our truss is 20 meters. Okay, next. We are given the load. Okay, just see here. How many load we are having? These are the insulation load and roofing load and insulation. Miscellaneous load we can also add. And this is self weight. So we are keeping the self weight separately and all the applied loads separately. Why? Because self weight is not producing the torsion, and all the other applied load which are acting at the top flange or the top surface of the purlin, they are also producing torsion along with bending moment. So just see here, 17 plus 5 is 22 and 12 is separate. So 22 is the applied dead load and 12 is the self weight. So these loads are in kilogram per meter square. So we need to multiply with the panel length or spacing of purlin, which is panel P value. If we are multiplying with the P value, so we are converting this distributed load into UDL load, just like we have discussed in the design guideline. So 22 multiplied by 2.5 and further multiply with 9.81. So this load will be Newton per meter square. and 12 multiplied by 2.5 into 9.81. This is also dead load or self weight, which is acting Newton per meter. All applied dead load and self weight we are dealing as a separately. Live load is 60 kilogram per meter. It is multiplied with panel length to convert into UDL and multiply with 9.81 just to convert into Newton. So that live load is 1472 Newton per meter. Total load is equal to dead load plus live load. So we are using service load because we are using ASD method. In ASD method, we are not multiplying dead load and live load with any factor of safety. We are just simply adding them up. So total load is the 540 plus 1472. That is the dead load plus live load. And we are dealing these self weight separately. Again, total load is this one, but again, we have shown the self weight separately and dead plus live load separately. Because this load will produce bending about y-axis and torsion, and this load will only produce the bending about y-axis. And the total load will produce the moment about x-axis. So mx, moment about x-axis. So we have to use two sag rods. How we have to use the two sag rods? Because we need to take the decision as per the instruction that are provided. If inclination of truss is more than 25, we will start designing by assuming two sag rods. So if we are using two sag rod, so if you will open the page number 79 on your LRFD design aid, so for two sag rod, we are having this table, page number 80. So our mx will be equal to omega cos theta s square by 8 and my will be equal to omega sine theta s square over 90. And force in sag rod will be 11 by 30 into omega sine theta into s. So from this page number 80, so mx will be omega cos theta by 8 into s square. So for mx, we have to assume total load. So total load including self weight, dead load, live load will produce the moment about the x-axis. But about the y-axis, we need to deal the self weight separately and total gravity load separately. So total load 2012 plus 295 will produce the moment about x-axis, which is 7555. And about y-axis, I have taken this expression from the page number 80. On the page number, actually, I think there's a numbering mistake. That is 80, page number. That's supposed to be actually the page number. Okay, page number 80. So omega y, movement about y-axis. So I'm computing two components of the movement about y-axis. One due to the dead load and live load separately, and one due to self weight separately. Movement about the y-axis due to the superimposed dead load and live load separately, because these loads are acting at the top of purlin and this load is acting at the center of the purlin. This load will produce bending moment about y-axis and also torsion. This mode will only produce the mode about y-axis and will not produce any torsion. So here 2012, this component is computed separately. Omega sine theta into L square by 90 and 295 sine theta into L square by 90. L is the length of the furlong, which is equal to spacing of truss. So I am having My. This is the My bending moment due to superimposed load, and this is due to self weight. And total My is equal to 387.71. And in this statement, we are asked to design as a channel. So if we want to design as a channel, so we have already seen we need to convert My and Mx into equivalent or assumed Mx. So Mx assumed will be equal to Mx plus 15 time of the My. So My multiplied by 15 plus Mx will yield the answer 13,371. So Sx required will be bending moment divided by bending strength, which is 0.66 Fy. So this moment is actually in Newton and meter. We need to convert into Newton and millimeter. So we are multiplying with 1000 because the unit for the stress is Newton per millimeter square. So Sx required is coming out to be 81 into exponent 3. So for the channel section properties table for channel section, which are given in LRFD design aid, you can look into design aid. I think the tables are given. They were DS section. They from the page number 69 to backward. So I want to select a section whose section modulus about x-axis is more than 81. So the option is coming. I will not select any MC or C, only C section. So on page number 66, I am having C in the second group, mid section C 115 to 15.6, 81. Actually, there is a mistake overwritten. So this is 82.9, and also on page number 65. So on page number 65, also we are having a section C200 into 27.9, whose section model about x-axis is 96. Anyhow, if you will select this, so for this section trial number 1, write down Sx and Sy. So check out the D minimum. D minimum should be S over 27.5. So length of furlong multiplied by 1000 divided by 27.5. So actually we need to select a channel whose depth is more than or equal to 200. So you will not select any channel section whose depth is less than 200. So that's why you will only pick the channel section whose depth is more than 200 and section modulus is also equal to or more than 81 into exponent 3. So based upon this criteria, we have picked this first trial section T200 into 12.6. Sx is 96 into exponent 3. Section modulus about y-axis 7.11 into exponent 3. Depth, actual depth is 229, which is more than D minimum. Just compute the bending stress. Bending stress we can compute mx over sx plus my over sy by 2, or you can assume that 2 times of my over sy, and then this is my over sy. So we will compute bending stress due to the movement about y-axis twice. So these are the bending stresses due to My about y-axis due to superimposed load, dead load and live load. These are this bending stress about y-axis due to self weight. So here we are not dividing the section modulus by 2 or multiplying the total factor by 2. So here we are using this multiplying this factor twice, because if this 2 is coming on the top side, so we have considered the torsional stresses. So torsional stresses will be produced due to the superimposed dead load and live load. And self weight is not producing any torsion. So we are computing the bending stress separately due to the self weight. And similarly, you can see here that due to the Mx bending stress due to the movement about x-axis, we have to consider total bending moment. And here we are just using the bending moment about y-axis due to the self weight due to the superimposed dead and live load that we have computed over here. So when we computed the total bending stress that are coming as 180.79, which are more than FB. FB is 0.66 FY. So we need to revise. So we need to select a little heavy section. Next available option. So next available option is seat 200 into 17.1. So for this case, section modulus about x and y axis given. So we will again compute the bending stress. Now the bending strength is coming out to be 113.51. And these are less than FB. Actually, there is some mistake over here. Maybe a repetition. So I will check what is the mistake. So I think there is some calculation mistake over there. So this answer is supposed to be less than 165. So I will check it later on. So this is supposed to be less than 165. So again, we need to check the BF over TF value. So the flange width of this channel is 57 divided by thickness of the flange 9.9. So this value answer is 5.76. So this answer is less than 10.7. So that is also okay. So again, we will check the self weight of the purlin. Is the unit weight of this channel, which is 17.1 kilogram per meter. So we will convert this load into the UDL load. So 17.1 multiplied by spacing of purlin, which is 2.5. Actually, here there is a mistake again in the calculation. So 17.1. How to compute this? 17.1 multiplied by spacing of truss, which is 2. Spacing of panel length multiplied by number of panel which are provided to us 8, and divided by total length of the truss. It will provide us the weight in kilogram per meter square. So we need to compare this weight against the assumed, which is 12 kilogram. So I will explain this again in the next lecture when we are starting. Or what you can do, you can convert the assumed purlin weight, which is 12 kilogram per meter square, into a UDL load by multiplying with spacing of purlin or with the panel length, which is 30 kilogram. So in that case, actual weight is 17.1 kilogram and assumed weight is 30 kilogram into multiplied by 1.2. So actual weight is less than assumed. So it means that we have already assumed larger weight, so that is okay. How to design the sag rod? So force in the sag rod. This is the force in the sag rod that can be assumed. So 11 by 30 into omega s omega sine theta. So this value actually we have taken from here. 11 by 30 into W sine theta into S is the force in one sag rod, in one purlin, at one purlin. Actually here you have to understand. So actually this force is coming at this point. On one side actually we are having how many purlin? 1, 2, 3 and 4. So we are assuming that this is connected from the one side. So it means that the force is acting at 3.1, 2, 3. So number of the purlin on one side minus 1. So we need to multiply this total force with the number of the purlin, because this force is acting at each point where the sag rod is connected in the purlin. So actually we are using three sag rods, 1, 2 and 3. So sag rod is the sag rod which is used between two purlin. So force in one sag rod is taken from the chart. So how many sag rods we are having on the one side? So if we are having 1, 2, 3, 4 purlin, so sag rod will be 1 minus or 1 less than the number of the purlin. So it means that if we are having 4 purlin on the one side, so we are having 3 sag rods. So force in one sag rod is taken from this chart. So this is the force in one sag rod. So force in one sag rod multiplied by the total number of the sag rod on one side will be equal to 5 minus 1. 5 minus 1 means number of the purlin on one side minus 1 will be number of the sag rod. So this is the total force in the sag rod, which is 9305. So we will convert into reaction in the sag rod. So reaction in the sag rod will be equal to R equal to F over cos theta. So 30 degree is the inclination of roofing system or top chord. So R value will be equal to 10,745. So here we are assuming that in the allowable stress design, so actually in the sag rod we are having tensile force. So we are assuming that this equation TA. So we are assuming this case TA tensile force should be equal to tensile capacity Tn divided by omega value, which is factor of safety in ASD method. So here we can further simplify this equation. So tensile capacity that is equal to we assume that the sag rod will fail in yielding because it is tension member. So we will have the area, the gross area of sag rod multiplied by Fy. And this omega value will be equal to, in ASD we are having the factor of safety 1.67. And this TA value is the applied reaction or the reaction force that we have computed. So from here, you can further simplify this. R is the tensile force in the sag rod. So one divided by 1.67 is equal to 0.6. Or from here, if area is unknown, we assume that gross area is the unknown value. Then that equation will be equal to R divided by 0.66 Fy. So that is the gross area required. So area is equal to pi d square by 4 because sag rod will be using as a circular rod. So area required is equal to R tensile force in the sag rod divided by 0.6 Fy. So R value we know, yield value of the material we know. So area we are assuming that area of sag rod will be equal to pi d square by 4. So only unknown will be diameter. So diameter will be used as a 10 millimeter. So I will stop over here. So in the next class, when I will start a lecture, so I will revise the design again. So we will solve another example for Perlin design. So in the meantime, if you are having any question, you can ask me. Any question? Roll number 56. 56.
Yes, sir.
57. 57. 58. 59. 60. Also note there 61. 62. 63.
Yes, sir. 63.
64. 65.
Yes, sir.
66. 67. 68. 69.
Yes, sir.
70.
Yes, sir.
71.
Yes, sir.
72. 73.
Yes, sir. Present.
74.
Yes, sir. Present.
75. 76.
Yes, sir.
77, 78,
Yes, sir.
79, 79, 80,
Yes, sir.
81, 80, okay, 81, 82, 83,
Yes, sir.
84,
Yes, sir.
85, 86,
Yes, sir. 86.
okay, 87,
Yes, sir.
88,
Yes, sir. 88.
89, 90,
Present, sir. 90.
90, 91,
Yes, sir.
92,
91. Yes, sir.
Yes.
okay, okay, हो गया 90, 92,
90. Yes, sir.
93, 94, 95, 96,
Yes, sir.
97, 98, 99, 100, 101,
Yes, sir.
102, 103,
Present, sir. 103.
okay, 104, 105,
सर 104 तक की है बस।
बस ठीक है, ओके यार। मेरे ये इस लेक्चर की रिकॉर्डिंग भी हुई है ये अटेंडेंस के साथ, और आपने भी नोट करने होंगे, ठीक है। ओके, इंशाल्लाह सी यू नेक्स्ट
एक्सक्यूज
टाइम।
मी सर।
हाँ जी बताओ, पूछे जल्दी से।
सर 72 डिस्कनेक्ट हो गया था।
चलो ठीक है, ओके, हो गई, आप बोल पर अटेंडेंस हो गई, ठीक है। ओके ओके।